So, good morning, all. Myself, Sajid Jamal Haq. I'm a PhD scholar in Department of Mechanical Engineering at IIT Madras. So, today I'll be talking about these principles of similarity and dimensional analysis. We'll discuss about a technique called Buckingham Pi-theorem, and we'll do some tutorial problem on that. So, this is the most important chapter in this fluid mechanics course, I feel, because using this dimensional principle, you can actually tackle very complicated problem, and you can understand the physical insights without even going through rigorous experiments or theory. So the outline of the lecture. So I'll be talking about the physical meaning and dimensional number, like how the dimensional number arises in a physical system. Then the dimensional analysis using Buckingham Pi theorem, and we'll do the problems and solution under dimensional analysis. Is my slides changing? Can anyone say, is my slides are changing?
No, sir.
Okay.
No, sir.
Now?
Yes, yes.
Yes, sir.
Yes, sir.
Okay. So these are the three outlines we will try to cover in this class. So we'll discuss about the physical meaning and the dimensional number. I think Sal had already covered few dimensional numbers, and then the dimensional analysis using the Buckingham Pi theorem. I will directly solve some problems and show it to you, like how to use this Buckingham Pi theorem to analyze a physical system. So if you see the different physical quantity, you will see that like mostly in fluid mechanics, we'll deal with the velocity term, which is like the unit is meter per second. So the dimension will be L1 and T minus 1. So wherever there is a 1, I am skipping that. I'm not writing the 1 to make it easier and make it more appearable. So the acceleration is like Lt minus 2, you know that, and the force, work and energy have the same dimension. Similarly, the pressure and stress has the same dimension, and dynamic viscosity, which will come in calculating the stress to this the strain rate ratio, and like if you want to relate the stress to the strain rate, we will have to invoke the dynamic viscosity. Then the kinetic viscosity is nothing but is the mu by rho. So its dimension is L2 T minus 1. So if you see the physical meaning of this dimensional number, we can start with something called the physical meaning of the diffusion. So in fluid mechanics, if you see the dynamical problems, it's all about like the convection and the diffusion. So the convection occurs when the flow happens, and the diffusion is because of the Laplacian term in the fluid mechanics, the Navier-Stokes equation. So we'll try to understand what is this diffusion and the convection, and try to derive some non-dimensional quantity out of this. So the diffusion equation, like in general for any kind of system, we can write as the flux of that quantity, whatever quantity we are talking about. The flux, if you're talking about flux, it is per unit area per unit time. The flux of that quantity is equal to the diffusion coefficient, and the change in the quantity, change in the density of the quantity per unit length. So in our case, in the case of fluid mechanics, this quantity is nothing but the momentum. So it will be like the flux of the momentum equal to the diffusion coefficient into the change in the density of the momentum per unit length. So So momentum flux, actually if you calculate the momentum flux, it is nothing but the stress acting on the fluid. So we are saying the momentum flux, that means m velocity, this is the momentum. So it should be per unit area and per unit time. So if you see this mvt, this is nothing but the force. So force per area is nothing but the stress acting on the fluid. So this momentum flux, if you want to relate the momentum flux using this definition, that is the momentum flux should be equal to the diffusion coefficient into the change in density of the quantity per unit length. So we know from the Newton's law that the momentum flux can be related to the strain rate. So here you can see one diagram where we have two parallel plates where the upper plate is moving at a velocity u. So because of that, the stress acting on this fluid, we can write tau ix equal to mu into this the velocity difference between these two plates divided by the length, which is nothing but the strain rate. So this one we have to like express in terms of change in density of this the momentum term of this quantity. So if you want to change that, you have to divide by rho and multiply by rho here. So this is nothing but the change in density of the momentum per unit length, and then we can get this mu by rho as a nu. So this nu is nothing but the momentum diffusion coefficient, or in fluid mechanics term, it's a kinematic viscosity. So so mu we can like nu we can say as a nu equal to mu by rho. So mu is the viscosity and rho is the uh, density. So it's called kinematic viscosity because it is not related to any dynamic, like it is not related to directly to dynamics. So if you see the dimension of this term, this is like L2 T minus 1. So it is meter square per second unit is. So similarly, we can talk about the convection. Like diffusion is all about this kinematic viscosity in fluid mechanics. So so convection, we can think of like let us consider a pipe cross sections where the fluid is moving at a uniform velocity of u. So if you take a cross section, I don't know why the slides are not changing properly. So this convection always we can define in terms of the mean flow. Like if we consider the mean flow in a pipe cross section as a u, so if we take the mass density as c, so then this flux due to convection will be the average velocity of the fluid into the this mass density c. So if you see the total amount of fluid transported because of this convection, it will be the average velocity u into the mass density c into the area of cross section of the pipe. So here you can see that the diagram, and where this pipe cross section area is a and the velocity is u. So the if the mass density of the fluid is c, then the mass flux due to convection will be u into c. So so depending upon this convection and diffusion, we can define this non-dimensional number. So this Reynolds number is defined as the ratio between this the momentum convection to the momentum diffusion. So momentum convection is given by the average velocity into some length scale, and the momentum diffusion is the kinematic viscosity. So ratio between this convection to the diffusion is the Reynolds number. So normally, like you can define Reynolds number in terms of force also. Like it is the ratio of the inertia to the viscous force. So that inertia to the viscous force and this momentum and convection and momentum diffusions boils down to this expression rho u L by mu. So L is the characteristic length. So in case of pipe of diameter D, so L should be replaced by D. Or in other problem, the characteristic length of the problem will replace that L. So there is another number known as the Smith number. The Smith number is similar to the Reynolds number, but it is the ratio between the momentum diffusion and the mass diffusion. So normally mass diffusion coefficient is written as capital D, and momentum diffusion is the kinematic viscosity. The ratio of this nu by D is known as the Smith number. So this will you can like study later in heat transfer or and mass transfer course. So next, the dimensional number involving the surface tension force or the capillary force. So so we can define like by comparing the different forces acting on a system. Like if you see in like small system like in microfluidics. So in microfluidics, in micron cell scale system, the viscous terms are dominant, and also there is a like capillary flow occurs in some small systems like in capillary tube. So in those cases we have to consider this capillary number. So capillary number is the ratio between the viscous force to the surface tension force. So this viscous force we can write in terms of mu u and like L, and this sigma into L is the surface tension force. So this characteristic length got cancelled, so it will be mu u by sigma. Similarly, the Weber number, it is the ratio between the inertia to the surface tension force. So inertia force again we can scale as rho u square L square, and surface tension force is sigma into L. So finally, one second. Finally, this L one L will get cancelled, and finally the Weber number will be rho u squared L by sigma. So this, I think, in the slides shared yesterday, there is a mistake. The Weber number is defined in terms of surface tension by inertia. So it's actually it is inertia by surface tension, not the other way. So similarly, like when we involve the gravity, uh, so the dimensional number we can express involving the gravity is again in terms of gravity. If you see, we can compare the inertial force acting on the particle. Uh, and the gravity force. So ratio of the inertia to the gravity force will give the call something called the Froude number, and this Froude number you can see this is like u square by gd. So here the inertia force will be rho u square L square, and this here d means the length scale. You can write L also in terms of d. So this rho z, it will come d cube or L cube. So the one two length scale will get cancelled, and z rho will get cancelled. Or finally, we can get v square by g d or g l. Similarly, the bond number is the ratio between the gravity to the surface tension force. And if you do the scaling, you will find out that this bond number is given by rho z L square by sigma. Sigma is the surface tension coefficient. So the Buckingham Pi theorem. Uh, so this Buckingham Pi theorem is used to analyze this system using the dimensional quantities and the dimensions. So if you have a system with n dimension and we have n dimensional quantities and m dimensions, so the difference between these two will give the dimensional groups. So we can find out the dimensional groups in a system. So the two important points for utilizing this Buckingham Pi theorem is the dimensional quantities we are taking that should be relevant to the problem. So it may be like we have like more than like we have more dimensional quantity in a problem, but in the problem limit or some physically it may not be relevant all the dimensional quantities. So you need to know the dimensional quantities that are relevant in the problem and the total number of dimensions that is used in the problem. So we'll discuss this problem, sphere settling in a fluid. So let's say there's a particle in the fluid which is settling under gravity in a tank of size L, and the sphere is moving at a velocity capital U. So the various forces acting on this sphere we can see here. It is the gravity force which is helping the sphere to settle down. Then the buoyancy force will act on the particle, and also there will be the drag force because of this motion, because of the fluid motion. So if you see this expression, we can write this Newton's second law for this particle, minus m du dt is balanced by this three forces. So we want to find out this the drag force acting on the particle using the dimensional analysis using the Buckingham Pi theorem. Uh, is it clear till now? Like, am I audible?
Yes, sir.
Okay. So if you see this, the force acting on a sphere, the drag force acting on a sphere, it was actually derived by Stokes. The Stokes drag force. It is known as the Stokes drag force. So anybody know what is the Stokes drag force acting on a sphere, which is having velocity u, and let's say the fluid viscosity is mu. So this drag force actually given by 6 pi mu r u, where r is the radius of the particle. Okay, so this one there is a rigorous derivation for this. So we'll actually find this expression without going through any kind of derivation. We can use this Buckingham Pi theorem and analyze the these non-dimensional equations and non-dimensional terms, and from that we can get this expression and we can get the this drag force. So here, what are the like dimensional quantities? Can anyone tell me that are relevant, like by seeing the expression or by seeing the physical particle motion in the fluid? So the dimensional quantities that are relevant here is the particle velocity u. So that means like if the particle goes faster, like velocity is more, then there will be more forces, and like more drag force, and vice versa. Those are like intuitively you can see that if the particle moving faster, that means the drag force will be more on the particle. Similarly, if the particle size is larger, the force will be larger. So the other is the size of the particle. Then similarly, the fluid viscosity and density will affect, and finally the length of the tank will also affect. So from here you can see the total number of quantity we are getting. Dimensional quantities are the 6 quantities: 1 2 3 4 5 6. So this is the n we got. Now we have to find out what is the m for this problem, the total number of dimension. So if you write down the dimension of each and every term, so for drag force, we can write the force dimension, and similarly we can write all the dimensions. So here you see this MLT, all three are present. So the total number of dimensions we are using this problem is 3. So the number of pi groups for this problem will be n minus m, which is n minus m is 6 minus 3. So 6 minus 3 equal to 3. So we have to have 3 pi groups which are non-dimensional. So we need to find 3 pi groups which are non-dimensional. And here, like if you see, it is very easy to define the first pi group, because we have a two term which are representing the dimension of a length. So one is the radius of the particle, other is the length of the uh, the fluid container. So if you take the ratio of these two, we'll get one. We already get a one non-dimensional term, the pi 3 term. So we don't have to do any kind of, we don't have to use any like calculations. So similar, secondly, we can define the pi 1 term. So pi 1 term we can define, see here, like we have how many term? We have 6 term total. So out of 6 term, we need to find the FD term. So FD we can take as a dependent variable, and we have other 5 terms. Out of 5 terms, 3 terms has to be repeating, because we have a dimension of 3. So 3 has to be like we need to have 3 repeating variables, and by that I'm taking this r, u, and mu as a repeating variable, and you have to balance these dimensions of this right hand side and the left hand side to find out the value of b, c, and d. So the dimension, the pi 1 term, I'm taking this pi 1 should be non-dimensional. So if it is non-dimensional, it should be m0, l0, t0 here. So for BCD, if you write the dimension of FD, R, U, and mu, so you can write the FD as the force dimensions, then R is the length, U is the velocity, and M is the viscosity. And then you can calculate this by balancing this the coefficient, that's 1 plus D, 1 plus B plus C minus D, and minus 2 minus C minus D. And you can put all this equal to 0 by seeing the left hand and right hand side. Then you can find that D is equal to minus 2, and C is minus 1, and B is minus 1. So you can find the pi 1 term as FD by mu UR. So this is the pi 1 term. So we have to have another second pi 2 term. So for the pi 2 term, again we are saying that r, u, mu are the repeating variable. So if we take r, u, mu as a repeating variable, we have to take another term which is there in the list, but which is not in the repeating zone. So we are taking the rho as the other variable. Uh, so if you use the similar dimensional analysis, we can find out this A, B, C using the same concept, and this A, B, C are turned out to be C is minus 1, A is plus 1, and B is 1. So if you use this, you will find out that this term pi 2 term boils down to u r by nu. So this u r by nu is nothing but the Reynolds number. So this boils down to Reynolds number. So if you see the first term, the pi 1 term has to be a function of this pi 2 and pi 3 term. So in that sense, we are getting f by mu ru is a function of ur by nu into r by l, like comma r by l. So now we have got a expression of this f or fd, the drag force, in terms of this function. So let's analyze if the particle is falling in an infinite medium. So if the particle is falling in an infinite medium, that means L tends to infinity. So in that sense, we can neglect the dependency of the drag force on R by L. That is the wall of the container doesn't affect the flow around the sphere. So we can write this FD me RU in terms of directly as a function of the Reynolds number. So Now we can see that this fd is a function of mu ru into function of Reynolds number. So this Reynolds number, in case of the very creeping flow condition, like where Reynolds number is very small, so inertial terms are small, so we can like approximate this Reynolds number in terms of some constant c, and this constant c you have to find out using some theoretical means or by experiments. So the Stokes-Drax formula, what Stokes proposed using the theory, is the fd is 6 pi mu r u. U is the velocity. So here we have obtained a similar expression, and the c we have to obtain from the experiment, because in dimensional analysis we don't exactly find out the expression, but we can approximate and get a scaling of the same expression. So if you see these terms, this is exactly same with the Stokes-Drax formula mu r u. So this is we talk about the this expression when the Reynolds number is very small. But what happens if the RE becomes very large? When the Reynolds number becomes very large, then we have to be very careful in choosing the dimensional quantities. So dimensional quantities always depends on the physical problems. So it shouldn't be like you're always selecting the same dimensional quantities for all the problems. So here, when the Reynolds number becomes large, we have to think that the viscosity is not important. So we don't have to take the viscosity as a term. So in this case, we have to consider the inertial term. So in the inertial term, we know already this density, the viscosity, the velocity, and the diameter of the particle will come into picture, and force is already there. So here, if you see that total dimensional quantities are n equal to 4, where the dimensions are fd, we have rho, then velocity, and the diameter of the particle. And if you write out the dimension of this 4, we'll get that m is equal to again 3. So we'll have m, l, t, all the three terms, all the three dimensions. So number of dimensional groups from this, if you see n minus m, it should be only 1. So that we can write as pi 1 is equal to f 1 and rho b uc and d small d. So if you write the dimensions and equate this power equal to 0, you will find that b is equal to minus 1, c is minus 2, and d is also minus 2. That means you are getting f by rho u squared d squared. This is the pi 1 term. So this pi 1 term has to be a function of the Reynolds number again. So for higher Reynolds number, we are getting the expression in terms of the inertial term. The viscous terms are neglected. So depending upon the problem, you have to you should able to select this dimensional quantities. Any doubt? You can stop me at any time and ask doubts. That is better actually. Then only it will be clear for you. Am I audible? Like anybody? Nobody's replying.
Yes, sir, audible.
Okay. You are getting the points, whatever I'm saying, or
Yes, sir. Yes.
okay.
Yes.
Next, one more problem 3, which talked about the this is based on the similarity solution. So the drag force, we need to find out the drag force on two spheres of different diameter, but the Reynolds number is given same. So if both the sphere are moving in, like one sphere is moving in air and other is moving in water, And if the drag coefficient depends on the Reynolds number, then we need to find out the drag force on the particle on the sphere. So we are given the ratio of the densities in the two fluids and ratio of the viscosity of the two fluids. So here they are saying that the drag coefficient. So the drag coefficient is defined as the drag force divided by half rho u infinity square into area. Okay. So the drag coefficient is the most important coefficient to find if you try to analyze the flow of a particle or a sphere in a creeping flow condition. So in that sense, you need to find out the drag acting on the particle, then you need to find out the drag coefficient. So they are saying that the CD in air equal to CD in water, because it depends upon only the Reynolds number. So Reynolds numbers are equal in the both the fluids. So the drag coefficients are also equal in this problem. So if you write the ratio of this, the drag force in air by drag force in water, so drag force in air will be the drag coefficient is air into the area into half of rho u infinity square. This u infinity is the velocity of the fluid without the particle. So if you take the ratio of these two, you say that this using this u infinity we can write in terms of Reynolds number this expression, and finally the Reynolds numbers are equal and the drag coefficients are equal. So this fd and a by fdw will come in terms of the ratio between mu a by mu w square and rho w by rho a. So if you put the values here, you will find out that this ratio is 0.281. Is it clear?
Yes, sir.
Okay, so next problem again we'll do a problem on this dimensional finding the dimensional term, non-dimensional term using the Buckingham Pi-theorem. So if you take a triangular notes, something like this, so the volume flow rate is given as Q in triangular notes as a function of the upstream liquid interface. So liquid interface is given at a height h measured from the bottom of the nodes. So this is the nodes, and this acceleration due to gravity is given as z, and the nodes angle is given as phi, and the approach velocity is phi. So using the Buckingham Pi theorem, we need to find the relation of this flow rate in terms of the other non-dimensional numbers. So if you see here, the dimensional terms are like we have flow rate, the height of the liquid surface, then the gravity, then the angle of the nodes, and the approach velocity phi. So we have total of 5 terms, and if you write down the dimensions of this all the 4 terms, so you will find that flow rate is given as L3t minus 1, then height of the uh, channel is given, it's a length scale, so it should be only L. Then the acceleration due to gravity it will be L1 t minus 2, and the angle like we know angle doesn't have any dimension, and the velocity is L t minus 1. So here only dimensions are relevant are L and T. So we have the number of dimensions are m equal to 2. So number of quantities are 5 and number of dimensions are 2. So the number of pi times required for this problem is also 3. So here we'll have only 2 repeating variables because m is 2, and that repeating variables I'm taking as c and h. So we have the pi1 term in terms of the flow rate. Because this is a dependent variable, we need to find q in terms of the other like non-dimensional terms. So similarly, you can write out the this dimension of each and every term, q, z, and h, and you can compare this power of these terms with the non-dimensional pi1 terms, which has a dimension of 0, 0. So if you write this, like if you solve this, you will get that a is equal to minus half and b is minus 5 by 2. So the pi1 terms will come as q by h to the power 5 by 2 and square root of z. Similarly, if you want to find out the pi2 terms, so we are repeating variables are z and h. So this is the velocity. So you write the velocity dimension, then z dimension and h dimension, and try to find out the power c and d. And this powers will come as d equal to minus f and c equal to minus f. So this pi2 term will be this velocity by square root of ch. So we need to find the last one more term. So if you see the pi3 term, we have this angle which is related to the this repeating variables z and h. So if you find here, both are coming as 0. So the phi doesn't depend upon other these variables. So the pi3 will be only phi. So we can write this pi1 in terms of this pi2 and pi3 as a function of pi2 and pi3. So pi1 is q by s to the power 5 by 2 square root of z is a function of phi by square root of zh and phi. So q we can write in terms of this function. So this function again we need to obtain through experiment only. So in dimensional analysis we can get uh, the we can go up to a certain extent. After that we have to do some theoretical means or experiments to find out the exact relation between q and the other non-dimensional terms. But finding the scaling we do in using dimensional analysis, it is very useful to understand how actually the flow rate will vary with the approach velocity or the gravity or the height of the elevated surface or the angle of the nodes. If you give we get a like gross idea how it is varying, and with that if you perform the experiments, it is very easy to find out the relation from the experiment. So that's the idea. So finally I'm doing a problem on this uh, similarity analysis. So we have a wave and eddy resistance of a sea-going level vessel of 96-meter length, driven at a velocity of 12 meter per second. So we need to determine the wave and eddy resistance. So for the purpose, a 1 by 16 scale model is employed in freshwater, and the coefficient of resistance is CWE of the model is found to be this much, 1.47 10 to the power minus 4. The quantity CWE is defined as FWE by half of rho V square L square. This is similar to the problem I did for higher Reynolds number flow. And this FW is the wave and the eddy resistance. And rho is the density, V is the velocity, L is the characteristic length of the problem, and the density of the seawater is given as 10206 kg per meter cube. So we need to find the towing velocity of the model and the resistance of the prototype. So here the prototype length is given as 96 meter, and the velocity of the prototype is given as 12 meter per second. So the length scale ratio is Lm by Lp. The scale model, the length scale of the model is given as 1 by 16 of the prototype model. So Lm by Lp is given as 1 by 16. So the coefficient of resistance of the model, that CWE, is given as 1.47 as 10 to the minus 4, and we have a uh, like we have a relation of relating the CWE with the FWE, which is nothing but the wave and eddy resistance. So density of the seawater is slightly higher compared to the normal water. That is 1026 kg per meter cube. So in the first problem, we have to find out the velocity of the model in the. So here for wave, the gravity force is the dominant force. So therefore, we can use the Froude number of the model and prototype. Uh, so we can find out the Froude number of the model and the Froude number of the prototype. We can equate both, and then we can find out the velocity of the model. So what is the Froude number? Can anyone tell me? Just now I actually discussed about Froude number.
The inertia by gravity.
Is it inertia by gravity? So if you write the expression, it will come as the velocity divided by square root of the gravity into the length scale. So from this, the other terms are given. So we know Lm by Lp ratio, then we know the velocity of the prototype. So we can find out the velocity of the model, the towing velocity of the model. So that is the first part. Then the second part is the resistance of the prototype. So the resistance of the prototype, again we have given this Lm by Lp ratio. So Lp is given as 96. So we can find Lm as 6 meter, the length scale of the model. So once you know the length scale of the model, so here what happened is the vessel is partially immersed in the seawater. So if you immerse anything in the water, it will experience the viscous force also. So the Reynolds number of the model and the prototype will be same in that sense. And once the Reynolds numbers are same, this CWE, the coefficient, will be a function of Reynolds number, and it will remain same for both the model. So actually we don't need to calculate the CWE. It will be equal to 1.47 and 10 to the minus 4. So here if you see this ratio FWE by half of rho v square L square. So this will be same for both the model and the prototype. The only thing will change is the velocity of the uh, model. So once you change the velocity of the model, the force acting on the uh, model will change compared to the prototype, but the ratio will remain same because the Reynolds number is same in both the cases. Is it clear? So once you got this coefficient of the prototype, then you can find out the force acting on the prototype using this expression. So the force actually will increase because your prototype length is higher compared to the model length. But if you see the ratio of this force on the prototype divided by half of rho Vp Lp square, this has to be equal to Fwe of the model and half of rho Vm Lm square. So the ratio will remain same, but the force acting on the prototype will increase. Any questions? Hello? So that's it for today's lecture. So any questions you can ask me. We have some time, 5 minutes. You can ask me anything you if you want, like apart from this course. Or should I stop now?